Okay, so I want to find the Fourier transform of x, f of x. This is a problem I'm working on now. I'm going to do it two ways. Method one is going to use duality, this kind of Fourier transform, inverse Fourier transform duality. So I'm going to recall the following facts. So recall that the Fourier transform of f prime of x is I omega times this is what so the Fourier transform of f prime is equal to I omega f hat of omega. Now, here's something I want to point out. We think about x as being like the main space variable, and then we take the Fourier transform of an x variable function to get an omega variable function. But that is just kind of a psychological distinction that we make. It's an important psychological distinction, but the math doesn't understand that psychological distinction. So from the point of view of the math, we could start with a function of omega and go to the Fourier transform of a function of x, or we can start with a Fourier transform in the x variables and do an inverse Fourier transform to get omega variables, just by swapping the variables around. Okay, so psychologically, these distinctions are important, but in terms of the math doesn't care about these distinctions. So note that we can change the roles of the variables. And I'll just make a little parenthetical comment here. The math doesn't know that we typically start with x and take the Fourier transform, start with the x domain is what I should say here, and take the Fourier transform to the omega domain. Whoops. So if we change the roles of variables, this means the Fourier transform of f prime of omega is equal to I x f hat of x. Okay, again, we're thinking about this weird sort of situation where we start with the omega, with the variable omega, take the Fourier transform and go to the variable x. Or equivalently, we could say, if instead of having f here, I have f check, so the inverse Fourier transform of f, or we can say that the inverse Fourier transform of I x f of x, because if I do hat and a check, that's just f, is check f prime of omega. Okay, we will use this. So if I just compute the Fourier transform, this right here is just the integral for the Fourier transform of x f of x. So it's e to the minus I omega x dx. This is equal to, okay, I'm going to do something a little bit different here. I'm going to put this with the omega there. I'm going to put a period as well. Okay, so what this is saying is, notice that this formula right here, this is the inverse Fourier transform. If I think about this, is the this integral right here represents going from the x variable to the omega variable as a Fourier transform variable. Okay, so these two integrals are equal. So forget for a second about this integral. These two integrals are equal. But if I look at just this integral here, this is the inverse Fourier transform. If I think about x as being the Fourier transform variable and omega as being the not Fourier transform variable, these two integrals are equal. It's just what our perspective is. This is the standard Fourier transform going from x variables to omega variables, but I can think about this integral here as being the inverse Fourier transform going from x variables to omega variable, so it's opposite. But the math doesn't care about that. Whether we're calling it the Fourier transform or the inverse Fourier transform, again, our perspective changes here in what's going on, but that's okay. The math doesn't understand that, okay? All right, so this is the inverse Fourier transform of x f of x, but evaluated at minus omega. So it is equal to, okay, so we talked about up here, the inverse Fourier transform of I x f of x is equal to this. Okay, so I only have an x f of x, so I need to divide by I. So this is going to be equal to fraction 1 over I. Let me just make sure that I'm doing this. I'm actually going to put some parentheses here. Here. This is okay. Okay, so now we want to look through a couple of things. So again, the inverse Fourier transform of Ix f of x is this. So if I divide both sides of this kind of equation, the is the equal sign. If I divide both sides of this equation by I get the inverse transform of x f of x is f check hat over I of omega. So that's what I have here. But the only difference is instead of evaluating it at omega, I'm evaluating it at minus omega. Now we need to be clear about what's going on here. What we're doing is we are taking the derivative of f check and evaluating that at minus omega. So we're taking the derivative of f check and evaluating that at minus omega. What we are not doing is we are not taking the derivative of the composition of f check composed with the negation function. Okay, so we don't apply chain rule here. Okay, so you can sort of think through this, using chain rule, saying if it was what I just said, you can get the following conclusion that I'm about to make. But I'm just going to compute it using the limit definition because we need to see what's going on here. Because I don't want the Fourier transform of f to be in terms of the inverse Fourier transform of f, or I don't want the Fourier transform of x times f of x to be in terms of the inverse Fourier transform of f. And I know I have this identity that says that the Fourier transform of f of omega is equal to minus the inverse Fourier transform at minus omega. Okay, so recall that hat f of omega is equal to check f of minus omega. Okay, so those two things are equal to each other. That was one of the things that we saw in class. It's basically just this formula here. That's where the idea comes from. So recall that the Fourier transform of omega is equal to the inverse Fourier transform of f at minus omega. So then what we're going to have here is the following. Okay, so if I just look at this right here. Okay, remember this is the derivative of f hat evaluated at omega. So this is the limit as h goes to 0. This is just the difference quotient. Okay, so up here, it's going to be, we're evaluating the derivative at minus omega. So I'm going to have a minus omega here, minus, and then minus omega here. Make that omega over h. And I'm just going to make this multiple lines. Okay, so now this is the limit as h goes to 0. And I'm going to use this identity here, that check f of minus omega is equal to f hat of omega. So this is going to be hat f. Okay, so it's going to be the negation of the argument here. So that's going to be omega minus h, and then minus the negation of the argument here, which is going to be like that, and that's going to be h. So let me compile this to make sure I haven't made any mistakes here. Okay, so now this right here, if you think back to calculus, here h is going to 0. If I put a minus sign here, I get a minus sign there. And now, so the thing is, I need, wherever I see an h, it needs to be going to 0 from the same side. So h here is going to 0 from the positive side. Well, if h is going to 0 from the positive side, h here is going to 0 to the positive side, but this is going for the negative side. So you might remember the fundamental the definition for derivative is there's a plus here instead of a minus sign. But if you have a minus and plus, that's negative the derivative. And maybe I'll just do one step to explain why that is. So this is going to be equal to the following. I'm going to put a minus h here. And now this is going to be plus minus h. Okay, so if we run that, if I multiply the denominator by minus h, I need to multiply the whole thing by minus h. So we're going to have this. Now this whole fraction here, right? If h is going to 0, then minus h is going to 0. So I can also change this to a minus h here. It's the same thing, right? And now this right here is the derivative evaluated at omega. Then I have the minus sign. And so this is equal to minus of omega. Okay. So then, the Fourier transform of x f of x, okay, the Fourier transform of x f of x is given by this integral here, which is equal to this, which is going to be equal to this divided by I. So let me go over that one more time. This is the Fourier transform of x f of x. That is equal to this. By this change in perspective, this is equal to this right here. Just this part right here is equal to minus f hat of omega. So then the Fourier transform of x f of x is minus 1 over I times hat f of omega, which 1 over I is equal to minus I. So 1 over I is equal to minus I, so this is just minus, or this is just I hat f of omega. Okay, now this duality thing is very handy if you can like have some proficiency with it. It gets a little bit complicated here. I understand that completely. I know it gets complicated. There's ways that we could write it without explicitly referring to the Fourier transform. I'm not going to keep it here, but there's ways we can write this without strictly, without writing the integral. I just did it here to make a little more sense. So we could have also said something like the following. F of x of omega. This is equal to the inverse Fourier transform. This is equal to the inverse Fourier transform of x f of x. So now this is like change in perspective. Okay, this function, but evaluate at minus omega. And then we could say from the fact that we know the inverse Fourier transform of omega f of omega, or x f of x, this is equal to 1 over I times prime, like that. We could have gone to the same spot there, so I'll just write that. So we could have used this fact without talking about, I don't know what happened. We could have used this fact without talking about, appealing to the integral explicitly. Essentially, the integral just explains this fact here, and I think it's a little more clear. At any rate, if you can get a good feeling for this duality, it makes computing Fourier transforms of functions easier. Like if you know that the Fourier transform of the derivative transforms to multiplication in the Fourier transform side, you can use that idea to figure out what the Fourier transform of multiplication is. Sorry, I get that's kind of confusing. This I still don't feel like I explained that like I want to. I think it's just something you need to sort of think about. It's actually taken me a really long time to make this video. One reason is because people keep asking me questions, which is fine. People coming into the office and stuff. But also I keep messing up how I want to explain it. But I'm just going to leave it how it is for now. Okay, here's method 2. Now, method 2 is a lot more straightforward, but it relies on being able to observe something, being able to make an observation. So first, note that, if you take the derivative of e to the minus I omega x, sorry, this should be omega. If you take the derivative of that with respect to x, what you're going to get is minus I, what you're going to get is minus ix e to the minus I omega x. Okay, so the derivative of e to the minus I omega x is equal to minus x e to the I omega x. So then, so it's going to be the same integral. We're going to start with the definition. This, sorry, phone is thinking. So this, okay, so e, if you look at this expression here, x e to the I omega x is equal to 1 over minus I times this. Okay, so, or I could write this as 1 over minus I times this is equal to this. So let me just compile this really quickly. Okay, so or 1 over minus I times the derivative of is equal to that. Now notice our integral has x times e to the I omega x. So what this says is this is equal to the integral. I'll just copy and paste. It's equal to the integral f of x times this expression right here, dx. Okay, let me just compile that to see how it looks. It's not going to look great. Okay, we're going to notice that 1 over minus I, remember 1 over minus I is equal to I, because 1 over I is equal to minus I. So this is 1 over minus 1 times 1 over I. That's minus 1 times minus I, which is just I. Okay. So this is equal to I times basically this whole integral again, but I'm just going to get out this. Okay, so now let's see what we have. Okay, this is good. Now notice our integration is with respect to x, but our differentiation is with respect to omega. Now, since f of x is, since we know our function is absolutely integrable by assumption, I mean, I didn't say it, but we're assuming that's just kind of a standard assumption that we're making for now. Since it is absolutely integrable, we can exchange the role, we can exchange the derivative with the integral. And so now this is going to be basically, not basically, well, it's going to be very similar, except I'm just going to move this derivative sign outside. Okay, so now what's going on here, this integral right here is the Fourier transform of f, and now we're taking the derivative, and so this is just equal to I times the derivative of the Fourier transform. Okay, that one is a little more straightforward in the sense that we're not having to, I'm going to use Leibniz notation here. This is a little more straightforward in the sense that we're not having to use that duality, but that duality idea is also important. It's also helpful, so that's why I did both of them. Okay, so there we go. Like I said, this video, in addition to the 20 minutes or so that it's taken me to actually make this particular video, this is like the 4th take or something, because I can never get exactly right how I wanted to explain it. Okay, I hope this helps. If not, please ask in office hours.